Okay, this, you don't have a copy of the handouts, and so this is just some notes about what to look at in your book to see. But anyway, we've done most of all of this stuff up to this point, and the extra examples we're going to work are going to be these particular ones from the textbook, so you don't have a copy of this unless you, I'm not sure, maybe you printed it in the ones I handed out. But anyway, we're going to look at these, and I actually just used the solution page. So we're going to work from there, so it's going to save us some time. So basically I'm pulling it from here. You can see this is our f of x right here, and it's going to be on this handout, and I apologize for the sloppiness, but basically if we factor the denominator, right, we find our discontinuities end up being 3 halves and -1. So to say where it is continuous means everywhere else, and this is interval notation for that. So just take your time, do a few of these. You should be comfortable with a good bit of this. So I'm just kind of touching and talking to you about some of it. This is just a polynomial, so it's continuous everywhere. Number 9 is the one in particular, the reason why I wanted to show you this. Okay, so if you remember about where things are continuous or discontinuous, and we talked about the domain of a radical, remember we say it's greater than or equal to 0 because we want this value to be positive. Well, that's how you say that. So we still factor, and we find out that the values are -3 and 2 when we solve this. And not only that, it's equal to. So what I do know is this. Okay, what I need to figure out is where do I shade this thing? So imagine that this wasn't shaded yet because we don't know that. So we just have -3 and 2 with solid circles. Okay, what we're going to do is we want to test some number, like if I divided this thing into 3 regions, I want to test this region, I want to test this region, and I want to test this region. Okay, so first let's start here. We want to test some number over here to the left of -3. Well, I just chose -4. I could have chose -5, -6, -7. It doesn't matter. I just chose one to the left of it. So plug -4 into here and evaluate and see if you get a true statement. So yes, we did. Because we got a true statement, I'm going to shade it. Okay. Next, here, I'm going to test something in the middle. Well, the easiest thing between a negative number and a positive number is pick 0. Let's make it easy. Plug 0 in everywhere there's an x, test it, and it comes out to be false. So I will not shade anything here. And then my last one, pick any number you want to the right of 2. I just went 1 to the right and test it. Plug it in. I got a true statement here. So because it's true, I want to shade. Okay. The shaded regions are where it's continuous, so we just name that in interval notation, which is going to be -infinity to -3 bracket, don't forget, because it's closed circle, and because of this equal to bar. Union 2 with a bracket to infinity. Good. Let me clear that. Alright, so we have a piecewise function here, and it says it's equal to the cubic function when it's less than or equal to 1, but it's equal to this function if it's greater than or equal to 1, and this is a smudged copy. So anyway, so what we want to do is let's consider the limit of f of x as x approaches 1. You can see both of these values are 1, so we're headed towards 1, but we're going to say to the left of 1. Well, to the left of 1, let's just think about this on a number line. To the left of 1 is less than, right? So that means this particular one. So we're talking about x cubed. Well, x cubed, let's plug in 1. 1 cubed is 1. Alright, well now let's take the right-hand limit. What's to the right of 1? Anything to the right of 1 it's going to be, it's the right-hand limit, so not headed that way. So we're going to come from the right, head it towards 1. So let's plug in, that's going to be greater than 1. Anything greater than 1. So to the right of 1 would put us using this function. So we want to evaluate this function at 1. So where x is, plug in a 1 and we find out that it's 2. If the left-hand limit does not equal the right-hand limit, then we say the limit does not exist, right? Yeah. So when the limits from the left and the limit from the right are different, it's a jump discontinuity, right? So now you can kind of start putting an image. And I'm going to clear this and we're going to scroll way back up to our image to a jump discontinuity right here, right? So that's what's going on. That's the visual for what's happening in our particular problem. So we would just say that it does not exist. We already know it's not continuous because first of all, if this doesn't exist, then it's not going to be continuous because it already fails one of the 3 criteria of the definition we started this lesson with, right? So it's not continuous at x equals 1. Alright. Okay, this one says show that f is continuous. Alright, first of all, let's just figure out where it's the continuous at, like this particular thing right here. Ignore this stuff over here to the right now. So first of all, because it's a radical, we're going to say 16 minus x is greater than or equal to 0. Negative x is greater than or equal to negative 16. We move 16 to the other side. If you divide both sides by negative 1, remember with inequalities, when you divide both sides by negative, you flip the sign. So it's x is continuous when it's less than or equal to 16, which interval notation would be this. Okay. The other thing, the limit of f of x as x approaches c. So put a c everywhere there's an x. So we want to put a c right here. Well, that just leaves us with this. Square root of 16 minus c. The other part of our definition of continuity is to say evaluate f at c. So this says go to the original function and where there is an x, plug in a c. So that would give us, okay, so when the limit of f of x as x approaches c, which is this, is equal to f evaluated at c, which is this, then you know it is continuous by definition. The last thing we're going to talk about is this intermediate value theorem, and I really suggest you look at the diagram on page 84. It gives you a visual and a picture for this, and basically it's showing if you have some value of function f of a and f of b, then there's some w in between it, such that this relationship exists. The f evaluated at c is equal to w for some c in a and b. And now that seems quite confusing, and I don't have the image in the textbook like I did in the other videos, so we're just going to kind of work with it. But basically it's the idea of something like if you're given an interval from a to b and of some function, let's just say that's our function, and f evaluated at a would be f of a, right? Function evaluated at a, some y value. And f evaluated at b would be some f evaluated at b. Okay, and what it's saying is if in between f of a and f of b there's some w, let's just say w in here. It could be anywhere between these 2 points. Then f of c, let me go backwards. There's some c in a and b such that when you evaluate it, it's going to equal to w. Basically, so if you have a point in between here and here and it's a continuous function, at some time you're going to have c, which is going to be equal to w. Let's just see it play out. I know that's a bit confusing, and it may help to look at the image in the textbook because it's a much nicer diagram. But anyway, they give us a function, so this is like the graph, and they tell us our a and b. This is negative 1 to 2. Let's go to our, okay, let's see, so let me kind of rough sketch, not precise by any means. So negative 1 and 2 is going to be our a and our b. Okay. In our function, if we drew this function out, you can put it in a graph and calculator if it makes you feel any better. And put it over here. But let's just use the properties. F of a is less than or equal to W, less than or equal to f of B. Okay, well f of A is -1, so f of -1, plug in -1 right here, and we get 0. So that's this calculation, so 0 is less than or equal to W. What is the f evaluated at 2? So we did that calculation here. Everywhere there's an x, we plug in a 2, and we got 9. So we know W is somewhere in between here, between 0 and 9. So there's some W there. Okay, our property in intermediate value theorem tells us that the f of c equals W. So we know this information. But let's go figure out what is the f evaluated at c. That means everywhere there's an x, plug in a c. So, right, that's just c cubed plus 1. Well, then now we're going to establish this relationship. W is equal to f of c. So W is equal to f of c, and that's this. And then all we're doing is algebraically solving for c. So subtract 1 from both sides, take the cubed root, and this is your c. The cubed root of W minus 1 is equal to c. So all that's saying is, if this is, let's just say hypothetically, that's W, then c is wherever your function is. Then we found the c in between the AB that fit this relationship using the intermediate value theorem. Like I said, if you were more precise and drew this actual function over here, you can see exactly, but this is what we're looking for. Alright, let's do it again. Alright, we have a new function, we have a new AB. F of A, right here, F evaluated at 1, that means go to your function, plug in 1 everywhere, and we get 0. 0. F of 3, our B is f of 3 is 3, so we do function evaluated at 3 is this calculation right here. Go to your function, plug in a 3, we get 6. We know our W is somewhere between 0 and 6. Then we also said, alright, let's go figure out what f of c is. Everywhere there's an x, plug in a c, and we get c squared minus c. Now let's plug in this over here. So W is equal to f of c. Well, f of c is this, so we say f of c. And solve this thing for c. What we want to do is get it equal to 0, and then now this is a quadratic. So we'll use quadratic formula, which is here. Plug in all your values. It's a little bit messy, but it looks like 1 plus or minus the square root of 1 plus 4w divided by 2. Yeah. So anyway, hopefully this helps and the volume works on this video, and all should be good.